This is Tiktaalik. It is one of the closest relatives to the tetrapods. Not an amphibian, but also not quite a fish. It's a remarkable animal, but before our ancestors got to this point, they had to go through a lot. This is an evolutionary journey from fins to limbs. After the Ordovician extinction and the start of the Silurian 443 million years ago, life on Earth recovered and diversified. Many different crinoids and corals came during the Silurian period. Reefs have existed since the Ordovician, but during the Silurian, an increase in shallow waters and temperature caused reefs and corals to see a diversification never seen before. And with this seascape looking more reef-like, there was plenty of life to accompany it. Trilobites, although hit hard by the Ordovician mass extinction, recovered tremendously and now cover the seafloor again. The trilobites don't even look too different from their Ordovician counterparts. The cephalopods also recovered, along with the armored nautiloids, but they are now no longer the apex predators of the ocean. These are the Eurypterids. They first appeared during the Ordovician, and now have taken their place as rulers of the ocean. They occupy many niches too, whether that be active predator or bottom feeder, and came to be found across the globe. They are even the state fossil of New York. The most common Eurypterid is Eurypterus, which makes up 95% of all known specimens. Eurypterids can come in many different shapes and sizes, with some being the size of your hand to others being as long as a man. To keep up with the Eurypterids, the vertebrates had to expand into new forms. Instead of just being jawless fish and filter feeding, in the Silurian, fish started fighting back and taking new forms. Fish evolved jaws around the early Silurian, and this evolutionary adaptation allowed fish to expand into many different forms. This is an example of a cartilaginous fish. It had flexible cartilage for a skeleton, and although they are small now, they will eventually evolve into stingrays and sharks. This is a placoderm, a now extinct group of fish that is characterized by its bony outside and teeth that aren't technically teeth, rather being sharp extensions of their skull. Although humble now, the placoderms will see great success in the next time period. And of course, there are bony fish. These include all fish today, excluding sharks and rays. Their main trait is, obviously, that they have a calcium-filled bone structure. And from the bony fish, we can split them into the lobed-finned fish and the ray-finned fish. Lobe-finned fish are most basically characterized by their fins having a paddle-like shape that is supported by a series of bones. This species, Goyo oranos, is one of the earliest known lobe-finned fish and measures at about 26 centimeters. In contrast, ray-finned fish have fins that are rounder and are more so supported by a series of bony rays. The Silurian was truly an age of fish diversification, where you can find most of the modern fish groups traced back here. But most of the fish were relatively small and weren't very close to competing with Eurypterids. At 1.2 meters, Megamastix is known to be the largest vertebrate of its time. It was a lobe-finned fish and was able to hunt various types of arthropods and vertebrates. Megamastix, though, was not the apex predator of its ecosystem. That honor would go to the arthropods. This is Pterygotus. It's another Eurypterid and is one of the larger species. At 1.75 meters, it's comparable in size to a modern-day crocodile. It's also thought to have inhabited oceans all across the world. For our ancestors, the open ocean has gotten more dangerous. With an array of sea scorpions and even other vertebrates, they weren't having it easy. But the general warming of our planet has melted the ice caps and raised the sea levels. This has caused lakes to form inland. Fish and some Eurypterids have taken refuge here from everything else in the ocean. And here, on land, we can find the first vascular plants. This is Cooksonia. Unlike the plants in the Ordovician, this plant has a vascular system. A vascular system is a series of tissues that transport water, minerals, and nutrients throughout the plant. This system allowed Cooksonia to be more advanced than the plants in the Ordovician. Plants still have a long way to go though, because Cooksonia didn't have leaves or roots. Cooksonia is also confined to areas near rivers and bodies of water. Cooksonia wasn't the only thing on land, as we have an entirely different kingdom, giant fungi. These fungi are called Prototaxides and measure at about 8 meters in length, and were technically the largest organisms in the Silurian. Because of these plants and fungi, we actually start to see the first land animals, and they weren't vertebrates. The first land animals were arthropods. This is a millipede. They originated here in the Silurian. They aren't exactly the modern species, but they are close. These may look like ticks or spiders, but they are actually relatives to them, and are called the Trigonotarbids. This is a true land scorpion. They are not Eurypterids, but arachnids. These animals, although small, are the base for all future land ecosystems. And maybe if they hadn't started to come on the land, our ancestors wouldn't. The Silurian was another remarkable time for life on Earth, and although the overall time period was short, being 25 million years, it's still a valuable piece of Earth's past, and that included remarkable evolutionary events like the appearance of jawed fish and vascular plants. And as we enter the Devonian, a time period that started 460 million years ago, arthropods will start seeing some competition, and our ancestors will head to the new frontier. During the Devonian, the supercontinent Gondwana was still intact and remained below the equator. It and a continent called Euramerica, which is made up of Europe and America, along with other landmasses, border the Paleotethys Sea. In the sea, plenty of shallow ecosystems exist. These requirements allowed reefs and life to flourish. Returning from its trip to lay its eggs, this is Cephalaspis. Although it may look like a new type of fish, it's actually closely related to the jawless fish we covered in the last episode. When fish evolved jaws, not all fish converted to the predator lifestyle. Some, like the 30-centimeter long Cephalaspis, chose to stick to an armored filter feeder approach. Unfortunately, the Eurypterids are still around, which makes the lives for jawless fish harder. The coral reefs of the early and late Devonian are built up by rugose coral. They are an extinct group of coral that have been around for most of the Paleozoic, and they now form the base for most Devonian coral reefs. Coral reefs around the Devonian globe were, of course, littered with trilobites, and you can find Eurypterids watching for prey. But some, like in the ancient Britain Sea, you can find plenty of jawless fish. Pteraspis is another strange armored jawless fish. It seemed to have a horn on its snout that could have been used for defense or perhaps sexual display. It measured at about 20 centimeters and might have eaten small invertebrates. This fish is called Trypanaspis. It sort of resembled Cephalaspis, but its eyes are a bit further apart. It was a pretty flat fish that could have grown up to 30 centimeters in size. It's thought to have behaved in filter feeding habits that are common with most of these kinds of fish. These fish are known as the ostracoderms and include the various types of these jawless fish that span from the Ordovician to the Devonian. There are plenty of these jawless fish that lived in the early Devonian that I wasn't able to cover. Though, in the ancient British waters, there weren't just jawless fish. There are also some jawed fish. One of those fish were named Tomacanthus. Tomacanthus was an extinct genus of spiny shark, a relative of true sharks. They measured up to 25 centimeters, and it's thought to have had shark-like scales. This fish is special in the fact that part of its brain case was preserved, which helps scientists understand the relationship between modern cartilaginous fish and their relatives better. Though, as the Devonian progressed, these types of jawless fish started to fade into relative obscurity, because during the Middle Devonian, the jawed fish started to take newer, deadlier forms. As we move through the Devonian, we start to see a power shift from the arthropods ruling the world to the vertebrates. And those vertebrates were, of course, fish. But not just any kind of fish, but rather the armored placoderms. We only briefly covered the placoderms during the Silurian because, like all other fish during that time, they were living in relative obscurity. But their armored forms, along with their jaws, allowed them to diversify and occupy whatever niches they could. Cocosteus was a relatively small placoderm, being about 40 centimeters long, and was an active predator. It's also part of the order of placoderms called Arthrodira, which all have multiple joints in their skulls that allow for a wide bite. Bothriolopus was a placoderm that vaguely resembled jawless fish, though, instead of filter feeding, it most likely used its small dentition to eat plants and small invertebrates. Meet Dunkleosteus, the 4-meter-long fish apex predator. Dunkleosteus had a bite force of over 7,000 newtons, or over 700 kilograms of force. Its bite force would have been 16 times stronger than a Nile crocodile, who today has the strongest bite force. This would give Dunkleosteus one of the highest bite forces for any fish. Not only could Dunkleosteus bite hard, but it could also bite fast. It may have been able to bite faster than the blink of a human eye. Dunkleosteus, like all their placoderms, did not have traditional teeth. Rather, it had bony protrusions that acted as a guillotine by slicing its prey into chunks. Dunkleosteus also had hard bony armor on its head, which basically protected itself from other Dunkleosteuses. Due to fossil evidence of Dunkleosteus bite marks on other Dunkleosteuses, it's thought that the species may have engaged in cannibalistic behavior, or at the very least, gotten into fights with one another. Dunkleosteus is by far one of the most impressive predators we've covered in Evolving Planet, having exceptional traits for an apex predator. It's also worth noting that, during the Devonian, an animal that is so common that it will eventually be more abundant than the trilobite appeared. This animal being the ammonite. Ammonites are a type of cephalopod and are surprisingly more closely related to cephalopods like squid and octopus than the armored nautiloids. Ammonites right now, though, aren't very diverse and are more fodder for Dunkleosteus to chow down on. The evolution of monsters like Dunkleosteus led to an increase in more heavily armored forms, like we see in the placoderms, and the competition from the placoderms drove most of the Eurypterids to relative obscurity by the end of the Devonian. Checking back in with the bony fish, we weren't exactly doing too great. Different types of lobe-fin fish were diversifying, but were pretty heavily outcompeted by their placoderm cousins. This pressure might have led lobe-fin fish to fill less heavily filled environmental niches. Eventually, one of those environments would be land. Since the Silurian, plants have started to become more and more complex. They now bear leaves, have roots, and they now reproduce via spores. Due to these advantages, and being generally better equipped to defend themselves against insects, plants outcompeted the giant fungal trees of the Silurian, and now make up the first true forests. Instead of being blue and brown, our planet is starting to look more green and blue. And now, with an increase in oxygen from the plants and food sources like insects on land, now was a better time than ever to go onto land. And in the rivers near these forests would give rise to some of the first land vertebrates. The first stage of the journey from water to land started with fish like Eusthenopteron. Eusthenopteron was a lobe-finned fish found in Canada that lived in shallow lakes. Its eyes faced forward to hunt other fish in the water. This fish existed 385 million years ago and wasn't too different from most other lobe-finned fish. Then, about 5 million years later, we would have fish like Pandritskis. There are some notable differences from this fish and our last one. It possesses less fins, and its face is a lot flatter, allowing it to see more above its head. It could probably temporarily haul itself onto land for a short bit, and if we looked inside its bone structure, its fins would possess more digits, which would be the blueprints for fingers. And now we reach Tiktaalik. It has the perfect mix of tetrapod and fish traits. Its fish-like traits include gills, scales, and fins. Its tetrapod-like traits include its ribs, neck, and lungs. It even has a mix of both fish and tetrapod traits, being termed fishapod, with traits like its limb and bone joints and ear region. It existed 375 million years ago and serves as a transitional fossil from fish to tetrapod. Although probably not being the true descendant to all tetrapods, it's evidence that these transitional animals from fish to tetrapod existed. It's probably one of the most important fossil discoveries ever. By the late Devonian, forests had spread across the globe. With little competition and almost limitless resources, trees had completely transformed the land. One of the environments forests had grown around was a relatively new type of ecosystem, the freshwater ecosystem. And in freshwater, you would find the product of millions of years of tetrapod evolution. This is Acanthostega. At 60 centimeters, it's a species of stem tetrapod and supports digits on its fingers. Weirdly enough though, it had 8 digits instead of the usual 5 we are accustomed to today. Acanthostega wasn't able to haul itself onto land, and instead primarily stuck to the shallow parts of lakes and freshwater ecosystems. Freshwater ecosystems of the late Devonian, though, held its own perils. In the Devonian, we can see many examples of primitive sharks. Stethocanthes was quite small, being about the size of Acanthostega. It possessed an anvil-like head display, probably used to attract mates. It also most likely fed on smaller animals, like certain fish and brachiopods. These basal sharks, compared to their modern-day counterparts, weren't very close to the top of the food chain, and weren't even that big. But this basic design for a shark would allow them to thrive later on and become top predators. Going back to the stem tetrapods, it's worth noting that despite seeming to have traits for temporary land dwelling, Acanthostega was a lot more accustomed to water. Its backbone and forelimbs wouldn't have allowed it to haul itself on the land, and despite having lungs, it also possessed very fish-like gills. Anthostega would have been very accustomed to hunting small fish and invertebrates. Unfortunately, it's thought that some species of placoderms were able to enter freshwater ecosystems, with species like Bothriolepis and Cocestius. Though, in freshwater ecosystems, the placoderms weren't nearly as dominant as in the oceans. Surprisingly, it would actually be the lobe-finned fish that would occupy the role of apex predator. Meet Hyneria, the 3-meter-long monster fish of the Devonian. Like I said before, it was a lobe-finned fish, and is one of the largest ever discovered. Its teeth were 5 centimeters long, and possessed large sensory canals to aid with its vision. With fish like Hyneria and basal sharks, freshwater ecosystems were starting to look more like the oceans when it comes to predators. This also meant that tetrapods like Acanthostega, being tied to the water, would have a lot to deal with. But some tetrapods were able to get a foothold on land, and one of those tetrapods were Ichthyostega. There were some key differences between Ichthyostega and Acanthostega. Ichthyostega had 7 digits on its feet, when Acanthostega had 8. Ichthyostega is also moderately larger than Acanthostega, being about 1.5 meters. It was also a lot more accustomed to land, having stronger ribs and vertebrae. This might have allowed Ichthyostega to feed on insects. Despite their differences, Ichthyostega and Acanthostega still shared some important similarities. Ichthyostega was still bound to the water, having thin skin like Acanthostega. So although it was able to go onto land, it was only in short bursts. Another important similarity is that both still have to lay their eggs in the water, as they would dry up on land. As stated in this segment, Ichthyostega and Acanthostega are both not true tetrapods, instead being stem tetrapods, which means they're closely related but don't have all the traits to be a true tetrapod. At the end of the Devonian, the vertebrates cemented the fact that they are now the rulers of the world, and will be for the remainder of Evolving Planet. But unfortunately, there would be another mass extinction that would cause a power shift among vertebrates. The late Devonian mass extinction is one of the least well understood extinction events, but there are various clues that point to the cause of it. The biggest clue is that animals in the sea were far more heavily affected than those on land, which meant that it had to be an event specific to the ocean. This means that the most likely cause for the extinction was a drop in oxygen levels due to various factors like volcanic activity and a decrease in temperature. This extinction caused a decrease in various invertebrates like trilobites, brachiopods, and various reef-building organisms. It also wiped out 96% of all marine vertebrates, which included 100% of all placoderms. Overall, this extinction wiped out around 70 to 80% of all life on Earth. But like I said, this extinction primarily affected marine organisms, which meant that our ancestors were relatively unaffected by the extinction, which makes it a good thing our ancestors decided to move on to land when they did. This leaves us at the start of the Carboniferous period, 359 million years ago. We are more than halfway through the Paleozoic era, with just 2 time periods left. The Earth is now covered with vast stretches of rainforest, and in these forests, the tetrapods will continue evolving to take over the world.